Hi everybody, this is a video showing a walkthrough of graphing and linearizing a quadratic function, and we'll show how to do min and max fits so that we can get the uncertainty in the slope and y-intercept. So I've made up some data here. This is not real IA data. It's made up. It doesn't matter, right? The data might look nicer than yours, and that's okay. We expect experimental data to have outliers and to not be perfect, and that's totally fine. I have some time and distance data here, and I have I've set it up so that the relationship that distance and time have is a quadratic relationship, a second order polynomial function. What's really important here is that this is a quadratic function where the b parameter is 0. This means that this graph is going to start its lowest value at the y-axis and then increase as the x value increases. If you have a full parabola as your graph, perhaps you're doing something with projectile motion, this would not be the correct way to analyze your data. There'll be another video for this. For that, I mean. So first, let's just make a graph. Let's make the regular graph of our dependent variable versus our independent variable. Let's add error bars to it. Let's add a trend line to it. And that's a good start. You have to do that. We want to see your actual, just straight up dependent versus independent variable graph. So to do that, I'm going to select my y values. I'm going to select my x values, and I'm going to hold Control on my keyboard and select my y values. Excel is going to assume that the column of data on the left goes on the x-axis and the column of data on the right goes on the y-axis. So it would be smart to type your data in that way so that you don't have to do anything kind of funky telling Excel, which data to use on which axis. I'm not going to show how to do that. Do it this way if you're not sure. We're going to go to Insert, and in the Chart section here, we are absolutely 100% going to do a scatter chart, an XY scatter chart. And we are absolutely going to select the scatter chart that has no lines connecting it. We don't connect the dots, right? We're going to add a trend line. We don't want to connect the dots. So I just click it, and my chart is done. Okay, it could be better. We could add a title. We should add a title. This is distance versus time. We should add axis titles. There you go. This is distance, perhaps measured in meters. No, let's say centimeters, just to be more realistic, but whatever, it doesn't matter. It's made up data. And let's say that these are times measured in seconds. Okay. That looks pretty quadratic to me. I mean, I made it so that it would be, so I hope so. Let's also add, before we add the trend line, let's add the error bars. Right now, when I add these error bars by default, I'm not sure what these error bars are. I didn't tell Excel what my uncertainties are. I'm guessing that this is like a standard percentage. Let's actually find out. So next to error bars, we're going to click this arrow and go to More Options. And they're going to show up over here on the right. I actually want to click on this option here, Error Bar Options. And so, first of all, we have horizontal error bars. That's what we're working on. You can see the horizontal ones are highlighted. We can click on the vertical ones to switch to those. In either case, actually, you got to click on one of the error bars, though. In either case, they're using standard error. I don't know what Excel assumes standard error is, but that's not what we want anyway. We know the uncertainty in our horizontal error bars would be time values. So we're going to go custom. We're going to specify a value, and it wants to know the positive error value and the negative error value, and ours are plus or minus the same thing. It's possible that you could get data where where it could be different amounts higher than lower. But that's not what we have. So the positive error value is going to be this set of data here. And Excel will know to put the 0.3 with the 2.0 and the 0.5 with the 4.0. And the negative error values are the same. I'll just select the same column of data. and then click OK. There you go. And you can see that the horizontal error bars are all different now. The uncertainty is made up too, but you can see that they're different. Let's do the same thing for the vertical error bars. And there we are. Again, not standard error, we want custom. And our Y values are distances, so we'll select this distance column 2 times. We want the positive and negative values to be the same. And we click OK. And there we have it. Right? Notice you can't really see the error bars, the vertical error bars in the first 2 points, so that might be a good thing to note in the text of your analysis. That the error bars are there, they're just kind of too small to be seen. You didn't forget to include them. Okay, so now let's add a trend line. And by default, it does a linear trend line for some reason, even though Excel should be able to tell which one is like right. So we go to more options, and again, we go over here to these bars, the trend line options. And I mean, we could play around with this if we're not sure. I know that I made the distance and time relationship be a polynomial order 2. That makes it a quadratic. And I don't know why my linear function, my linear fit keeps staying there. So I'm just going to select it and press delete. And now it's gone. And so there we have a really nice quadratic fit. And if I click on that again, I can choose to display the equation on the chart. And I can make that bigger. Now you'll notice I said this was specifically for where the B parameter was 0, and Excel's not giving me 0, but it's giving me 2 times 10 to the negative 13. That's 0.0, a lot of zeros and then a 2. That's essentially 0. So I'm actually going to go in here and delete it. And if you wanted to talk about how Excel gave you something that was very, very small and essentially 0, you could explain why you're removing it and why you're justified in doing so. If I really wanted to be good, which I guess I do, I could say that my Y values are times. I can say that my X values are, my Y values are distances. My X values are times. I know that my Y-intercept unit is centimeters. And what would this be? If I'm going to multiply something by t squared and get centimeters, then the second squared I get from t squared have to cancel. So this unit would have to be, let's put this all in parentheses. This would have to be centimeters per second squared. So that when I plug in seconds and square it, and then multiply by 1.2 centimeters per second squared, all the seconds cancel, and I'm just left with centimeters because I know that this is an equation for distance. Maybe I should have called that displacement. I'm not that concerned. So we have our equation. And I'm not going to bother putting the R value on. I made up this equation. The R value is going to be 1. So we're not really concerned. The point is we have our quadratic graph. We have the equation of that function. And that's great. Like, this would be really good if this for some reason is all you could get up to on your IA, and you could say that the relationship is quadratic and here's the equation for it, and you presented it this way where you replaced Y and X with a D and T and you included units on those parameters. That would be really good, but we could do better. And the reason is that A parameter, 1.2 centimeters per second squared, I mean, you probably recognize those units as an acceleration, right? As acceleration units. And that must be the acceleration of the object that I'm investigating here. And that acceleration is probably an important experimental value that is based on measurements that we took that have uncertainty, distance and time, namely. And so this acceleration should also have uncertainty. I don't know that it is exactly 1.2 centimeters per second squared. Likewise, I guess if the C parameter is 10 centimeters, that would be the distance when the time was 0. That must be the position where this object started. And maybe we know that with a high degree of precision. But if we're learning it from this graph, it's based on all those time and distance measurements, and it has uncertainty. So we have done a lot, and this is really good, but we could definitely do better. So if we are confident that this is a quadratic function, then what we want to do to linearize it, instead of plotting distance versus time, we want to plot distance versus time squared. Now we have a bit of work to do before we can make that graph. So I'm moving this chart over, and I'm going to highlight all this distance stuff, and I'm going to drag this over 2 columns. Now, if you drag it like that, any equations you have in there, or any equations that depend on those cells will move with it. So if you're graphing processed data, you should be able to select a bunch of cells and move them basically wherever you want. So I'm going to make a new column here for time squared, and I'm going to have time squared uncertainty. And my time squared is literally just going to be those times squared. So I'm going to say equals, and then I'm going to select this cell, and I'm going to raise to the power of 2. Oh, look at that. 2 squared is 4. I knew that, but I can drag this down by clicking on this little square in the bottom right corner and do all of that squaring automatically. Here's the harder part. We need to figure out what the uncertainty in the time squared is. So if you want to look on your data booklet, there's a rule for how to figure out the uncertainty, how to propagate uncertainty when you are raising a value to a power. In this case, raising it to the power 2. And the rule is, I'm going to see if I can write this out in a cell just so that you can see it. And then I'm going to have Excel do the calculation for me. The equation as written on your data booklet for this is delta y over y equals n times delta A over A. Now, y is our time squared. Delta y is our uncertainty in the time squared. A is the thing that we're squaring, which is time. And delta A is the uncertainty in the time. N is the power to which you are raising it, which in this case is 2. Okay, so, and this is a percent uncertainty calculation. So if I do 2 times the uncertainty in the time divided by the time, and then you could think of it as like cross multiplying with the y, I would get the uncertainty in the time squared. And that's what I'm going to do. And if you want to make sure that that makes sense, I encourage you to take the equation from the data booklet and write it out on paper, and maybe double check my calculation. See if you can get mine manually so that you trust that what I'm doing in Excel is right. So to do any calculation in Excel, you always start with equals. And I want to do 2 times, and I think I found that you can't just put 2 things next to each other for multiplication. You have to use the asterisk to tell it to multiply. So 2 times, open parentheses, we want to take the uncertainty in A, which is the time uncertainty. We want to divide that by the value of A, which is the time itself. I want to close parentheses. So I hope you can tell that right there, so far, I have the right side of the equal sign. N times delta A over A. And then, to solve for delta y, I'm not trying to solve for delta y over y. I want delta y itself. That is the uncertainty in the time squared. I'm going to multiply by the time squared. So times this cell. And let's hope this works. Enter. Okay, 1.2 out of 4 seems like kind of a big uncertainty. Maybe I made up big uncertainties for this, and that seems okay. Let's select this and apply that same calculation to all these other cells. This is one of the main reasons to do anything in Excel. Okay, if we want to be really good here, which I guess we do, we should change the precision of these so they match the precision of the time squared. Are the time squareds right? If I square time, they have 2 sig figs. It's time times time. That's weird to say. Time times time. The answer should have 2 sig figs. Well, some of those have 3. I don't care. I'm going to leave it the way it is, even if it's not exactly right. Don't tell anybody. But I am going to move the decimal point here so that the time uncertainties, the time squared uncertainties are to the 10th place because the time squareds are to the 10th place. Okay, so that's the setup for this. So I'm ready to plot distance versus time squared, which as long as this relationship is really quadratic, should give us a linear function. And so that's what I'm going to do. I'm going to select the time squared values, and I'm going to hold control on my keyboard and select the distance values. And again, Excel expects the column on the left to go on the x-axis and the column on the right to go on the y-axis. And so I've done that. Insert, XY, scatter, and we want the one with no lines, please. And there we have it. That looks pretty darn linear to me. Let's do the same stuff. Let's change the title. Let's do distance versus time squared. Let's add axis titles. This is distance again in units of centimeters. This x-axis is now time squared. And if we squared those times, 2 seconds times 2 seconds is 4 seconds squared. Let's make sure we have those units correct. And, okay, let's add error bars. That's an important thing. So add error bars. And again, Excel did the standard error thing. We don't want that. So let's select some error bars. Let's go over here to what does this say? Error bar options. We're on horizontal, which is x squared. So custom, specify value. These are the uncertainties in our t-squareds. That's the positive error value. It's also the negative error value. And then we click OK. And so we see our time uncertainties. Then we can select our y values. We want to do custom there as well. Our distance uncertainties are our error bars, positive and negative. And we click OK. And there we go. Nice linear function. Looks like it anyway. Error bars are there. Maybe they're pretty big. Maybe I should do a better job of measuring my time. Or I should make up better numbers. It really doesn't matter. I'm just kind of joking. Anyway, let's add that trend line. And we're going to make sure that we select linear. We want linear. And we want to display the equation on the chart. And I'm going to make that larger so we can see it. Whoops. Oh, no. Now I did it. Let's Control Z that. Okay. We have something that looks pretty darn familiar. Except this is written as a linear function. Because guess what? It is a linear function. But when we go through and change things, when we update what's on the y-axis and what's on the x-axis, and when we put units in, we'll see that it is going to match, in this case, exactly the equation from our quadratic graph. So on the y-axis is distance. On the x-axis is time squared. Time squared. Okay. I could probably make it go up there in the, can I make it go up there in the superscript? I don't know. I'm just going to leave the caret symbol there. That's fine. And our slope of 1.2, slope is y divided by x, y values divided by x values, which would be, in this case, centimeters divided by second squared, centimeters divided by second squared. And our y-intercept, right, is a y value, so that would be centimeters. And, wow, check that out. It's a little too big, actually. We have d equals 1.2 centimeters per second squared times t squared plus 10 centimeters. It is literally the exact same equation. Now, okay, pause for a moment. Mine is exactly the same equation because I made up my data. Okay? So yours might not be exactly the same, right? Your slope might be a little bit different than what you get from the quadratic trend line. And your y-intercept might be a little bit different. And that's okay. We're going to go with what shows up in your linearized function. Okay. This is great. But actually, to be honest, we haven't accomplished anything more than what we had before, right? We have the equation. What we really did this for was so that we could find the uncertainties in that slope and y-intercept value. Those are the parameters of this equation. Or since it's a quadratic, you could say it's the a and c parameters. So linearization is done. Now we need to plot our minimum and maximum fits. So we need to figure out what data points to use to plot our maximum fit and minimum fit. And I'll be honest, right now, I'm just going to do exactly what Chris Donner did in his video because I think he explained it really well. And I'm just explaining it again so that it's part of this comprehensive video. Okay, so our maximum fit line should be the steepest line that fits within the error bars of our data. And so to get a really steep line, we want to start at the bottom right corner of this data point down here. Right? You can picture any of these data points has like an uncertainty box around it. And any data point, any coordinate, I should say, within this box is a possible value for that data point. And so if we go from the bottom right of this first point to the top left of this last point, we'll get a line that is going to be not a good drawing, I think. That is a pretty steep line that fits within our error bars. Okay, let's stop there and do that one. This data point over here has an X value that is to the right of the data point itself. It's X plus the uncertainty in X. The Y value of this coordinate in the bottom right corner is below the Y coordinate of the data point. It's the Y coordinate of the data point minus the uncertainty in the Y value. This data point up here is, I guess, the opposite. It is to the left of the data point. It's the X coordinate of the data point minus the uncertainty in the X. And it's above the Y coordinate. So it's the Y coordinate plus the uncertainty in the Y value. And so what we need to do is give Excel two data points. We need to give Excel a distance. Nope, that's wrong. A time squared and a distance that matches this math here. And then we also need to give it a time squared and a distance that matches this math here and tell it to make a best fit line, to make it a linear trend line starting at the first point and ending at that last point. Let's give that a try. I realize now that I should have been a little bit more careful maybe because, well, I don't have a lot of space. So let's do down here. Let's do the maximum fit, and let's do the X coordinate, the X coordinates of it, and the Y coordinates of it. All right. So the first data point, the bottom left data point that this maximum fit is going to go through, is going to be equal to the first X value, the first time squared value, plus the uncertainty in the X value, the uncertainty in the time squared value. Enter. The Y value is going to be the Y coordinate of that first data point, which is our distance, and it's going to be minus the distance uncertainty. Okay. The next point that we're going to make this go through is this top point, the top left corner of the top data point. The Y coordinate of that is going to be equal to the X value of that last data point, 144, minus, because it's to the left of the data point, minus the uncertainty in that data point. And then the y value is going to be equal to the y coordinate of that data point plus, because it's above, plus the uncertainty. And enter. Let's see if this works. So here's what we have to do. We don't want to make a new graph. What we want to do is add this line to that graph. And I'm going to get rid of this drawing in a second. Let's see if we could put the maximum fit line on there and see if it kind of matches what I hand drew. So we're going to go to insert. No. First, we're going to select our data. Now, since they're next to each other, I don't have to select them as separate columns. I can select this whole group. I think I'm doing the wrong thing. Hold your horses there. So here's what we're going to do. We're going to select the chart that we want to add. Uh-oh. Now it's all messed up. We're going to select the chart that we want to add to, and I'm going to go to chart design. You can also right click and go to select data. I was going to go to chart design and then select data here, or you can right click on the graph and go to select data. And there's already one series of data on there. We want to add another series. We want to add series name. We could call this max fit. And the X values are these two X values. And the Y values are these two Y values. And let's click OK. And then let's click OK again. It's hard to see because I kind of drew it right in the right spot. I think there's a data point there and a data point there. Let's see if I can erase this drawing, this writing that I did on the screen. Okay, it's gone. And you can see those two data points in just the right spot. So now I am going to select that data. I think it's selected. It's hard to tell if it's selected. Anyway, let's right click on it. Let's see if it works. Does it work? Uh-oh. Oh no. What's happening? Oh, I'm on a drawing tool still. Well, that's silly. Let's go back to this cursor. Let's go home. Let's just go home, everybody. Okay, can I do it now? Boom, selected that data. I'm going to right click on that data and I'm going to select add trend line. And it's linear. Great. And I want to display the equation on the chart. Fantastic. And let's give this a name. This is going to get messy. So let's call this max. And what we're going to get from this is our maximum y slope and our maximum y-intercept. Actually, we're going to get our maximum slope and our minimum y-intercept. And that's exactly what we expect. I'm not going to go through the trouble of editing this and calling it d and t squared. We're just trying to get that 1.645 and that 4.7459 value. We're not going to necessarily show this equation. Let's edit this one to call this one best. All right. Okay, good. I guess it would be worthwhile writing out the math for the minimum fit. So let's do that. Let's go. What are we doing here? Draw. And let's do a different color this time. Let's do green. Okay, so to get the lowest slope line, we want to go to the top left corner of this first data point to the bottom right corner of this last data point. And it should give us a graph, a line that looks something like that. Okay. I'm going to go a little faster here, but I'll still explain what I'm doing. I hope that this makes sense. This data point is to the left of the X coordinate. So it's going to be X minus the uncertainty in X. And the Y value of this top left corner is above the Y coordinate of that data point. So it's going to be Y plus delta Y. And over here, it's on the bottom right. So the X value of this data point here, this bottom right corner, is the X value of that last data point plus the uncertainty. And because it's below this last data point, its Y value is going to be the Y value of that data point minus the uncertainty in the Y. Okay, and so let's go ahead and do that. So this is minimum fit, and we're going to have X and y. And the first point, the x value, is going to be the first time squared value minus the uncertainty. And the y value is going to be the first distance value plus the uncertainty. And then the last data point is going to be the x value of the last data point. Whoops, got to do equals first. Equals the x value of the last data point plus the uncertainty. I'm hitting weird keys here. Give me a second here. Equals the x value of the last data point plus the uncertainty in the x value. And the y value of this bottom right data point, this bottom right corner, is the y value of the last data point minus the uncertainty in that point. There we go. Now, one thing that should be true is that none of the coordinates that you're using for your maximum and minimum fit lines should be the same. So in case you added when you should have subtracted or something like that, just look at these data points. None of these numbers are the same. That's just something that popped into my mind just now. If we did this right, none of those data points should be the same. And like I said, if you accidentally added the uncertainty when you should have subtracted it, you'd have a duplicate number here, and we should not. So I'm going to get rid of the drawings first because I don't so much like them, and delete those. Now let's get to this chart. No, I'm still on the drawing tool. Son of a gun. Let's get the cursor. Okay. So we're on the graph. We're going to right click and select data, or go to chart design and select data. We're going to add another series. Let's call the series minimum fit. And the x values are these two right here. And the y values are these two right here. And when we click OK, oh, look, they're already there. Those two gray data points. Awesome. And now let's select those two gray data points and right click and add a trend line. And of course it should be linear. And we want to display the equation on the chart. And I'm going to make it bigger. And I'm going to put minimum, min, in front of it so that we remember that's what it is. Okay. So we have our best fit for our linearized data. We have a maximum fit for our linearized data. And we have a minimum fit for our linearized data. And like I said, I'm not going to go in and add units to these. I'm not going to go in and change the y's to d's and the x's to t squares because we don't need them for that. So let's talk about what we can do now with this information. So we have a greater slope here in the maximum fit that falls within the error bars, the uncertainty of our data. And we have a smaller slope that also fits. And same thing with x and y intercept. And so we can figure out the uncertainties in those things. Let's make a little chart so that we can talk about this and actually follow what we're doing here. So let's put the minimum and the maximum and the best, and then let's put the uncertainty. And I'll explain what we're doing here. So let's move this around a little bit, make this a little bit neater. Let's move it there. This chart could be a little smaller, don't you think? So let's do slope, and let's do y-intercept. So our lowest slope that we can get is 0.9016. Now, by the way, we should probably be concerned with the precision of this value. So we didn't calculate the slope ourselves, but the y values have a certain number of sig figs to them. The x values have a certain number of sig figs to them. When we divide y values by x values, which is what slope is, we should have some... we should be able to figure out how many sig figs our answer should be. It's probably not 4 sig figs. I didn't really plan for this, so that can be something we talk about another time, or you can figure out for yourself. The maximum slope from our linearized data and our max and min fits are 1.645. Our best is 1.2. Now the uncertainty in that is going to be half the range. So the maximum, well, let's just do it. All right, let's do open parentheses because we want to do a difference and then a division. So the maximum value minus the minimum value, close parentheses, divide by 2. There we go. We have our uncertainty. Our y-intercept, you know what? Let's make that one match the precision at least. Let's move the decimal point to the 10th place to match the 1.2 that we have for our slope. So it's going to round to 0.4. Great. The minimum y-intercept is 4.7459. Notice that the minimum y-intercept comes from our maximum fit, and that's to be expected, actually, if you think about it. And our maximum y-intercept is 13.776. Our best y-intercept is 10. 10? 10 point, should be 10.0? Should be 10.0, right? Let's call it 10.0. And then the uncertainty is half the range, right? So equals, open parentheses, maximum minus minimum divided by 2. And again, let's move the precision so that it matches 4.5. This is pretty high uncertainty. I made up uncertainties that were around 10% for the original measured value. So, I guess that compounds. I mean, this is big. We're done now. So we have the equation right here. The equation that relates our dependent variable to our independent variable is d equals 1.2 centimeters per second squared times t squared plus 10 centimeters. Not only do we know that relationship, but we also can say, we wouldn't write it in the equation, but we can say in our analysis that the slope is 1.2 plus or minus, and it would be better to use the plus or minus symbol if you can, 0.4 centimeters per second squared, right? So in this case, we know that this slope value represents the acceleration. So the acceleration of the object is somewhere between 0.8 and 1.6 centimeters per second squared, right? We think it's 1.2. It can be anywhere within that range though. And the y-intercept is 10.0, not 1. What'd I do? Let's get rid of that. Let's fix this. Plus 10.0, please. Plus or minus 4.5 centimeters. Right? And we know that the y-intercept represents like the initial position of the object. Right? So it started at position 10 centimeters plus or minus 4.5 centimeters, which is pretty big. If this was an experiment where I started something at the 10 centimeter mark of my meter stick for some reason, and then I ended up with plus or minus 4.5 centimeters, I would probably discuss that. I would probably point out, like, I know that I placed it at the 10, and of course there's some uncertainty in that measurement. But this plus or minus 4.5 centimeters comes from the propagation of the uncertainty and from the analysis from the graph. So I think that's it, right? This would give you a lot to talk about. You have your result. You even have uncertainty in the parameters of the equation. And what's important about that, and I hope I've made this clear, the parameters of this equation, call it the slope and y-intercept, or call it the a and c parameters of the quadratic, which we kind of originally started with. You can still see that guy over here, right? Those numbers have what we call physical significance, right? And I've explained what that is. The slope here is the acceleration of the object, and the y-intercept is the initial position. That means something, right? That's why I always say that they have to have units. They represent something in real life that will be measured in some, scientific units. And also because they are They're calculated values based on measurements that have uncertainty. These calculated values cannot be perfect. They also must have some uncertainty. And we did it, right? So you probably don't have distance and time. You have, who knows, some other pair of variables. It might not be as obvious what your slope and y-intercept mean, right? Try to figure out what the units would be for them and try to think about what they could mean. And I would help you with that if you need it. And then this is where this is right at the transition from the analysis section to the evaluation section. So at the end of your analysis section, you should be able to state what equation you get relating your dependent and independent variables, and you should be able to discuss what the uncertainties are in the parameters. And then at the beginning of your evaluation, I think, is where you would discuss the significance of the equation and the significance of the parameters, the physical significance of the parameters, and you might mention the uncertainty at that point as well. I think I'm done. We've been going for about 40 minutes. I hope this is a useful walkthrough. Please give me feedback on this, and don't just give me positive feedback. If you try to follow this walkthrough and it's not helpful, please tell me so I can make a new one, or I can make this one better, or something else, right? Feedback is always appreciated. Please don't hesitate. If it's critical feedback, that's great. Just be nice. That's it. Good luck with your IA. I'm sure you'll do a great job.